What is the pH of a 0.10 molar ammonium chloride solution if the Kb of ammonia is 1.8 times 10 to the negative fifth? I'll give you a second to copy that down. And then I want you to think about what kind of salt do we have? You know, is it a neutral salt, an acidic salt, or a basic salt? Hopefully you figured out that this is an acidic salt. Why is it an acidic salt? Well, if we look at it, chloride is a terrible base. Ammonia is the conjugate acid of the ammonium, NH4 plus is the conjugate acid of the weak base ammonia. So ammonium is actually going to be acidic. So hopefully you figured out we have an acidic salt. So now you need to show this being acidic. We need to write a formula for doing that. Now I'll give you two options. Okay, option one, NH4 plus gives back its H plus and makes NH3. That's option one. Or you can show NH4 plus and water making H3O plus and NH3. So remember, H plus doesn't really exist, but all of us self-respecting chemists, we know that it exists. So you pick how you want to write that out. I'll go with this guy. Okay, the top one. Doesn't matter to me. Okay, so we got an acidic salt here. So how are we going to get the pH of this thing? Well, you can see once we figured out what kind of salt we have, and once we've shown it being acidic, now the rest of it is going to fall into place. Okay, we'll write our mass action expression. We will make an ice table. We will do all that awesome stuff. So here we go. We have an acid. It's making H plus on. So we're going to write our mass action expression. Ka equals H plus times NH3 all over NH4 plus. We need a Ka, and we have Kb. That's okay. Y'all can fix that. Go ahead. Get Ka from that Kb. Take a minute. So how do we get Ka? Well, Ka times Kb equals Kw. So Ka equals Kw divided by Kb. Ka equals 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. And we get 5.6 times 10 to the negative 10th for our Ka value. So now we can make an ice table. So we can do ice. Our initial concentration, it's 0.1 molar NH plus. No NH4 plus. X and X. Now we're going to plug that stuff on in there. 5.6 times 10 to the negative 10th equals X times X over 0.10 minus X. I'll give you a second to catch up. Again, you know, more you practice it, you almost become robotic with it, right? Now, can I make the X's small? So I take my smallest initial concentration divided by that constant. The answer is going to be, oh, yeah. Yup. X is small. So now we're going to multiply both sides by 0.1. We get 5.6 times 10 to the negative 11th equals X squared. We're going to take that square root. x equals 7.45 times 10 to the negative 6. We're probably stuck with 2 sig figs. So let's do 7.5 times 10 to the negative 6th. That is my hydronium ion concentration. I wanted the pH. So pH equals negative log of 7.5 times 10 to the negative 6th. And that's going to be 5.12. It's always good. We said this is an acidic salt. It's always a good feeling to get an acidic pH when you're done. That always feels good, right? So, yeah, I mean, it's a lot of work, okay? It's like an extra step at the beginning to get your mind right. You got to look at the salt, and you really have to take a minute and make sure you figure out what kind of salt it is. This is an acidic salt. Conjugate acid of a weak base is going to be decently acidic. The conjugate of something weak is decent. So decently acidic salt. We had the KB of its conjugate. We had to get its Ka. And then it's off to the races, mass action expression, ice table, plug and chug. Let's try another one. How about this guy? I would like, this one's going to be more difficult because it's the other kind of salt. What is the pH of a 0.8 molar sodium fluoride solution if the Ka of HF is 7.2 times 10 to the negative 4th? Here's what I want you to do, just so we can kind of chunk it. I want you to figure out what kind of salt it is. Once you think you know what kind of salt it is, show me its acidic or basic part reacting with water. Write an equation. Go ahead. All right, hopefully you figured out this is a basic salt. Why is sodium fluoride basic? Sodium is the conjugate acid, or it's an alkali metal cation. It's the conjugate acid of strong base, sodium hydroxide. So that's a non-existent acid, but fluoride is the conjugate base of the weak acid HF, meaning fluoride is a decent base. So hopefully you figured out it's a basic salt. That's the first step in this process. Next thing you have to do is show me that basic salt being a base in water. So we're going to show fluoride reacting with water. It's going to rip a hydrogen off of it to make HF and hydroxide. Just like that. There we go. Cool. Now I want you to give this a shot. I want you to write a mass action expression. I want you to make an ice table. I want you to see if you can't solve that thing. Don't forget, that's the Ka of HF. You need the Kb of F minus. Good luck to you. You got this, guys. See how far you can get. Worst you can do is get it wrong. All right, folks. So we hopefully got up to here where we have our KB expression. We have our ice table. Now we're going to plug that stuff in. I'm going to throw that trailing zero back on that 8. It's bothering me. There we go. So we're going to plug this stuff in. We need to get our KB here first, though. So KW divided by KA equals KB. So KB 1 times 10 to the negative 14th divided by 7.2 times 10 to the negative 4th. And we get 1.4 times 10 to the negative 11. So here we go, folks. 1.4 times 10 to the negative 11th equals x times x over 0.80 minus x. And now we need to see if we get rid of that minus x. 0.80 divided by 1.4 times 10 to the negative 11. That is definitely greater than 500. X is small. That means we get rid of that. And now the math gets about 1,000 times easier. We get 1.1 times 10 to the negative 11th. That equals x squared. Take the square root. X equals 3.3 times 10 to the negative 6th. We are on the home stretch here, folks. What is X? X is the hydroxide ion concentration. I want the pH. So hopefully you're starting to get back into the swing of things. We can get the pOH very easily. And we get 5.48. And now 14 minus that gets us the pH. The pH is 8.52. Here's another great feeling. You ready? We said this was a basic salt. At the end, you better get a basic pH, right? And we did get a basic pH. It was 8.52. Never a good feeling. If you predicted it was a basic salt, you do a whole bunch of math and you get an acidic pH. That is not good, right? Something went wrong, and then you got to try to figure out what went wrong. That's a basic salt. We did end up with a pH above 7. Okay, these take a little bit of practice. Okay, they take some practice. Buffer problems have salts in them. So we'll talk about kind of how that works, and especially when we get to weak acid, strong base titrations, because the equivalence point is one of these problems as well. So what happens when you have a complex salt? So what do I mean by a complex salt? Well, that would be something like this guy. Okay, if we look at this is what I call a complex salt, and this is going to be above the scope of our class. You would cover something like this in analytical chemistry if you majored in chem, usually about your junior year. This is an acidic cation. It's the conjugate acid of the weak base ammonia, NH3, and that's a basic anion. It's the conjugate base of the weak acid, acetic acid. So, this should decrease the pH. This should increase the pH. Who's going to win? Well, this is actually a special salt. The Ka of acetic acid is the same as the Kb of ammonia. So that means that the Kb of acetate and the Ka of NH3 would be the same. So this guy's actually neutral. Now it just happens to be very special, so such that this is as weak of an acid as this is weak of a base. So the conjugates will have the same strength of one another. So that's just a special scenario. They don't they like never work out like that. Let's look at number 2 for an example. Again, a complicated salt. That's an acidic cation. That's a basic anion. So what does that mean? Well, if we go down here and we look up the Kas, HCN has a acid association constant of 6.2 times 10 to the negative 5th, and NH3 has a Kb of 1.8 times 10 to the negative 5th. But I actually need cyanide's Kb. So I want to know what's cyanide's Kb. And I need ammonium's Ka. What's the Ka of ammonium? So we need to do the Kw thing, 1 times 10 to the negative 14th divided by 6.2 times 10 to the negative 5th. So the Kb of cyanide is 1.6 times 10 to the negative 10th. And the Ka of ammonium, that's going to be 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. That's going to be 5.6 times 10 to the negative 10th. So what do we got here? Well, ammonium is slightly more acidic, 5.6 times 10 to the negative 10th, than cyanide is basic, 1.6 times 10 to the negative 10th. So ammonium is a slightly better acid than cyanide is a base. So what can we do? Well, we can make a prediction that this pH will be slightly acidic, but very slightly acidic. Now, what am I not going to ask you to do? I'm not going to ask you to solve for the pH here. Okay, you do not have to solve. That's too complicated. That's something you would do in analytical chemistry. However, you should be able to tell me that's a complicated salt. Okay, it doesn't have chloride, bromide, iodide, nitrate, perchlorate. Doesn't have an alkali, earth metal, or ammonium cation. So both of those ions will affect the pH. If I give you the Kas and Kbs of the weak acid and weak base, you should be able to get the Kbs and Kas of the conjugates. And then whoever is stronger, that's the one that will impact more. You can see here, ammonium is a slightly better acid than cyanide. We can predict it's slightly acidic. What is it? I don't know. Is it 6.5? Is it 5.2? Who knows? Okay, we'd have to do all kinds of crazy math to figure that out. And we need to know the concentrations.